So the next talk is by Mansi Dhuria, and she'll be talking about self-interacting neutrinos, unified path to dark matter and cosmological tension.
Okay, good morning. Am I audible? So I would like to thank organizers for giving me this wonderful opportunity. And the title of my talk is Self-Interacting Neutrinos, which could be unified path to dark matter, which is sterile neutrino dark matter and cosmological tension. And yeah, so the part of this talk is based on the work which has been done in collaboration with research student Abhinas Pradhan. Okay, so yeah, so this is outline of my talk. So recently there has been a lot of discussion about the possible nature or possible interaction of standard model neutrinos with each other. So the normal intuition is that standard model neutrinos do not interact very strongly with other rest of the particles in standard model and even with each other. So then this is a new discussion that it can interact strongly with each other and they can have huge effect on early universe cosmology. And the main idea behind this discussion is that the self-interacting nature of standard model neutrino can help to reduce or even remove the Hubble tension, which has been discussed by Anuprita very nicely. So this is basically the discrepancy between the value of Hubble constant measured by early universe by CMB observation and low redshift based experiments. So this is about the effect of self-interacting neutrinos on cosmology. And recently the sterile neutrino has also self-interacting nature of standard model neutrino has also gained attention in producing KV sterile neutrino dark matter, which is one of the interesting warm dark matter candidate. Yeah, so the in the standard scenario, sterile neutrino, KV sterile neutrino warm dark matter candidate has been ruled out by X-ray observation. Almost the entire parameter space has been ruled out. And we are going to see how by considering these self-interacting standard model neutrinos, we can have a lot of parameter space without getting into X-ray constraints. So in this part, so I'm going to talk whether the allowed masses and interactions that we are considering for self-interacting neutrinos to reduce Hubble tension, that is also in agreement with the one which is required to produce KV sterile neutrino dark matter, because we are getting very precise data from cosmic microwave background analysis. CMB observations are getting more and more precise. Any complementarity or agreement between each other will give us, will help us to get to explore more about signatures of this warm dark matter candidate. So I'll summarize results and various constraints, and then I'll briefly discuss the theoretical framework where we can realize these masses and spectrum of parameters which is needed to explain this. Okay, so okay, so what we understand in standard model, we have three generations of active neutrinos. We have electron neutrinos, muon neutrinos, and tau neutrinos. And the general understanding is that neutrinos interact very weakly with the standard model particle as well as with each other. And we also understand that neutrinos play a very crucial role in early universe cosmology. And we have understood that results from CMB measurements have put stringent constraint on the absolute mass of some of neutrinos, which is less than 0.12 electron volt. So with this motivation that neutrinos has been playing an important role in cosmology, there is a new phenomenological model which has been motivated entirely from cosmology. We consider new interactions of neutrino with a new scalar, with a new particle, which could either be scalar or it could be a vector mediator, because this doesn't really affect the cosmology. So this is the interaction of neutrinos with the new mediator, which for heavy mass of mediator, at least greater than MeV, could lead to Fermi-like interactions of neutrinos with each other. So this is the 4 Fermi interactions of neutrinos. So, okay, and Now we are what we have understood, that neutrinos, because of its weak interactions, they get very freezed, they get frozen, they get decoupled in the early universe very early. So it's at very high redshift, neutrino starts decoupling from the early universe because of its weak interaction. And this can be understood as follows. So if we can here, so if we write this effective coupling, we can represent this effective coupling by G effective, which is G square by M phi square. This is G, the coupling of neutrino with mediator, and M pi is the mass of the mediator. Okay, so now we are going to see how this effect on the free streaming nature of neutrinos, if we consider these new interactions. This is the thermal average scattering cross section of neutrino, which scales as G effective square. And we can calculate the neutrino interaction rate in the presence of new self interactions of neutrino, which again scales as G effective square, and T nu 5, which is the temperature of the neutrinos. And this plot, if you see this plot, this is y-axis is the time evolution of the interaction rate of the neutrino to the expansion rate of the universe, which can be calculated by calculating the opacity of the neutrinos. And there, if we consider G effective equal to usual Fermi coupling in standard model, which is the usual coupling, then we would see that this is on x-axis, there is redshift. We can see that it becomes 1 at very high redshift of the universe, which is between 10 raised to power 10 and 10 raised to power 9. So, so this tells us that if we consider the usual weak interactions of neutrino, it gets decoupled at very high redshift of the universe. However, if we increase this interaction because of this new mediator that we are considering, which is actually physics beyond standard model. So these are the two specific values or specific regions of the interaction that has been considered, and this has been done in series of papers, and once very specific values have been obtained from the CMB analysis. This is called this is strongly interacting mode, so where G effective is 10 to the power minus 1.86. So it is basically the coupling is around 0.1 to 0.01 if we consider mass of mediator around MeV, and this is moderately interacting neutrinos. We can see that neutrinos are if we consider this interaction, neutrinos are in thermal plasma till late redshift of the universe, till 10 raised to power 6 and 10 raised to power 5. And if we consider this very strongly interacting neutrinos, then it is it does not get decoupled even, you know, it gets decoupled just before BBN or something, because we don't want to disturb the constraints from BBN. So the understanding is that if we consider these new strong self interactions between neutrinos, then we can delay the redshift at which neutrino starts decoupling. And now we are going to see how this affects on cosmology. And this the CMB analysis of by considering this self-interacting nature of neutrinos has been done in a lot of papers. These are the references. So what eventually happens? So this is one plot that I've taken from this paper. So this is the baryon acoustic oscillation power spectrum of CMB, and this black point is the lambda CDM behavior. This is if we don't consider any self interaction between neutrino, and if we consider all three neutrinos of standard model to be interacting with thermal plasma till late redshift, we can see that there is slight change in the amplitude of the baryon acoustic oscillation. There is a slight change in the amplitude, but this is still a good fit to CMB. If we don't consider all neutrinos to be interacting, but consider either 2 or 1 to be interacting, then also we can see this shift in the amplitude. So basically, why would this shift happen? If neutrinos are not free streaming, so this will increase the gravitational potential in CMB, which could change in the amplitude of the photon perturbation, and that's why we can see this change. In addition to this change in the amplitude, we can see a little shift in the phase of the peaks. So there is a slight shift in the phase of the peak that we can see. And this actually helps us to think about how we can use this change to get a different value of Hubble constant. So let me explain this. This is the phase shift of the baryon acoustic oscillation of CMB power spectrum, phi nu, which depends on this ratio R nu, which is the number density of neutrino to the number density of photons and neutrinos. If we do not have much, if we do not have that much number of free streaming nature of neutrinos, then this R nu gets decreased. Okay, so rho nu is the energy density of free streaming neutrinos, and this gets decreased, which would lead to decrease in the phase shift. And CMB multiple for a particular, this position of the peak depends on this phase shift like this, m pi minus phi nu. dA star, RA star, this is the radius of sound horizon, and dA star is the distance to last scattering surface from today. So now, if phi nu decreases, we can see if phi nu decreases, m pi minus phi nu will increase, which could lead to the change in the position of the peak. If we want to keep the position of the peak to be same, to have good CMB fit, this can be compensated by increasing either increasing the value of dA star or decreasing the value of sound horizon. So the distance to this dA star, this depends on Hubble expansion rate like this, and similarly this is the speed of sound, which depends on Hubble expansion rate. So now, because this this distance dA star depends on the low redshift, where actually there is no domination by matter or radiation, if we slightly increase the value of Hubble constant, if we slightly increase the value of H naught, then we can have a good effect on, we can increase the Hz without having much effect on the speed of, on the radius of sound horizon, because that will be dominated by radiation and matter radiation. So we have, so this small increase in the value of H will decrease the value of dA star, which can compensate the increase in the increase which we have got due to this phase shift change. So this is how, this is one early universe solution. So like Anuprita has discussed that there could be early universe as well as late universe solutions to the Hubble tension. So this is one possible solution which can be accommodated by considering the self-interacting nature of neutrinos.
Where does the self-interaction come in?
Self-interaction would change the free streaming nature. So this is where, so rho nu is the energy density of free streaming neutrinos.
So there will be just the energy density in the mass plus you adding a potential in the rho nu.
No, so basically because of self-interaction, what we understand that it is, we understand where it gets decoupled. So this, at the redshift where we are doing this calculation, so this is not decoupled. So that's why this is the energy density of free streaming neutrino, which we use in CMB. So there would be change in this at different redshift that we are considering. So like, because this CMB power spectrum will take into account how many degree of freedoms of neutrino we have at early.
So later decoupling.
There will be a later decoupling. Okay, so this is the idea that has gained attention. So okay, so this is Hubble tension. So okay, fine. So the basically the detailed analysis has been done in these papers, and they have come up with this very specific values of G effective. This is called strongly interacting region, and this is called moderately interacting region, and we have got very specific region of the effective coupling. So, and this effective coupling can be recalculated into the couplings of G phi and M phi. So basically, if the mediator that we consider is of MEV, then the coupling could be 0.1 or so. Okay, so now these new couplings that we have introduced, G phi and M phi, these are subjected to various laboratory and cosmology constraints. And these constraints have been calculated very precisely in this paper. So this is the constraint on G phi and M phi parameter space by considering, the first plot is by considering all the universal coupling, that all three neutrinos, electron, muon and tau neutrinos interact universally, at the same level with this mediator. And this is flavor specific constraints, that only electron is interacting to the mediator, or muon is interacting to the mediator, or tau neutrino is interacting to the mediator. These blue lines, blue regions and green regions are the moderately interacting coupling, G effective, that has been calculated from the Hubble tension requirement. And we have seen that this entire region has been, entire region of Mi nu and Si nu is constrained from various laboratory constraints, various decays of kaons and all these things, and the requirement from cosmology. the neutrino cannot be, if the Dirac neutrino, if we consider the Dirac nature of the neutrino, that will have some, that can have some effects on the delta ineffective, and there are constraints from this. So basically we see, if we see all these constraints, even this entire region is ruled out, this entire region is ruled out. We have this substantial amount of parameter space that is left for tau generation of neutrino or moderately interacting G effective. So this is one good, interesting parameter space which could be explored more. And also we have some constraints from IceCube that could be used to explore more about these couplings. Okay, so this is the idea as far as Hubble tension is concerned. Now I'm going to talk about the effect of self-interacting nature of neutrino in KeV sterile neutrino dark matter. Okay, so what we understand in particle physics when we are talking about new physics beyond standard model, the choice of sterile neutrinos, sterile as the name suggests, these are the additional neutrinos that we consider, which interacts even more weakly with the thermal plasma, so it has very feeble interactions that we consider. But these are very interesting particles that we consider because they are needed to generate observed baryon asymmetry of the universe. They can explain small mass of neutrinos. And as it has been discussed in morning talk, viable warm dark matter candidate are also is one of the interesting choice to address the small scale structure anomalies of the power spectrum. So it is, if we consider this sterile neutrino, we can have KeV scale sterile neutrino as viable warm dark matter candidate. And this can address also some of the short baseline anomalies in neutrino experiments. So what happens? So basically there are 3 standard model neutrinos. And if we consider new physics beyond standard model, we take 4th neutrino, nu S, which can also get mixed with the active neutrinos, the standard model neutrino. So this is basically 4th mass eigenstate, which is combination of sterile neutrino and standard model neutrino. So if we have this, if we consider this sterile neutrino as dark matter, we can see that through this one loop diagram, this sterile neutrino, through this mixing with standard model neutrino, this can decay into photons and standard model neutrino. So this is the decay, nu S going to gamma nu A. And this gives us observational signatures of KeV sterile neutrino dark matter. Because we have chosen mass to be KeV, this can be observed through various X-ray observation through X-ray telescopes, because the energy of X-ray would lie in KeV. And if we calculate the decay rate of this sterile neutrino, this depends on the mixing angle between active and sterile neutrino, is theta, and the mass of sterile neutrino. So if we choose the mass of sterile neutrino to be KeV and mixing to be very small, this tells us that the decay width is quite high. So basically, we can expect very slow decay of sterile neutrino going into photons, and which can be observed by X-ray telescopes. And the non-observation of dark matter has also put constraints on the mixing angle and mass of sterile neutrino. Okay, so now if I talk about the production of sterile neutrino dark matter, the very standard mechanism that has been adopted to produce the dark matter is what was proposed in late 90s, which is Dodelson-Vitro mechanism. So this basically, what we understand that sterile neutrino cannot be in thermal interaction with other standard model particles because of its feeble coupling. So this cannot be produced in the early universe. It has to be produced with some small mixing angle. However, if we see that as these standard model neutrino propagate through thermal plasma, we know that neutrino can have these oscillations. So we can acquire, because of this oscillation, we can also acquire the sterile neutrino component. We can measure the probability of getting active neutrino converted into sterile neutrino based on the mixing that we have. So this is how we can calculate the production of sterile neutrino. This is the distribution function of sterile neutrino as a function of temperature. This depends on the active neutrino interaction rate, and this depends on the probability of active neutrino going into sterile neutrino. and depends on the distribution function of the thermal distribution of the active neutrinos propagating in the universe. So the probability of active neutrinos getting into sterile neutrino depends on various parameters. So this delta is just mass of sterile neutrino square by energy. And we would see that this actually depends on the interaction rate of active neutrinos. So what we see that interaction rate of active neutrino is playing very important role. If we have to calculate the probability of nu A going into nu S, this is going to have an important role. And this is the matter potential. So when neutrino is doing the oscillation, we can also calculate the matter potential. Okay, so if we do not have any standard model, any self-interacting neutrinos, so this is the interaction rate from the standard model. Okay, and this is the matter potential. We can calculate the matter potential using these Feynman diagrams. And then we can calculate the relic abundance of sterile neutrino, which depends on the relic density of sterile neutrino, which can be calculated from the number density of sterile neutrino by calculating this distribution function. So this distribution function will give us a number density, and then we can calculate relic density and relic abundance. So this is the results. These are the results from this standard Dodelson vitro mechanism. So this red line corresponds to the parameter space where we can explain the right value of dark matter. And this is the region. So this light brown region, if you see, this region is entirely excluded from X-ray observations. So we can see that this almost the entire parameter space of KeV sterile neutrino dark matter that you can obtain through Dodelson vitro has been ruled out by X-ray observations. So this was the result. The model is good, but it has been ruled out. Okay, so now so this mixing angle, okay, so this mixing angle is there, right? So this, this is the allowed mixing angle versus mass. Okay, so now that, let's say we are assuming self-interacting nature of neutrinos, and we have these new mediators because of which these neutrinos interact. These neutrinos, this interaction, so we will have new interaction. So this is the interaction in standard model, where interaction is through this weak interaction. And these are the new interactions where we can produce the sterile neutrino through the new interactions of new with mediator based on the similar thing that we discussed in cosmology. So we have new interaction rate of producing active neutrinos and so far and sterile neutrino. So we have new contribution to the interaction rate. Gamma is gamma standard model, gamma phi and conjugate. And these are the limiting expressions of the interaction rate in different limits if m phi is greater than T or if m phi is less than the temperature. And similarly, we can calculate it has been calculated in these papers, the matter potential in the presence of these new interactions. Okay, so yeah, so these are the results. That has been, this is which is there in this paper. So basically, if you consider this new interactions, they have considered this as lambda phi. This is the plot of the relic density for a specific value of sine square theta, 10 raised to power minus 11, and mass of sterile neutrino 7 keV. This 7.1 keV mass of sterile neutrino has become famous due to observation of 3.5 keV line, which is still an issue, and I am not going into that. So we can, okay, so based on that, they have also scanned the parameter space of sine square theta in this entire range as a function of sterile neutrino mass from 1 to 1000 keV. This is the result from Dodelson vitro, right, that we had seen. And it has been seen that we have, one can have a lot of parameter space. This entire white region is the parameter space that can give the correct value of dark matter, KeV sterile neutrino dark matter. So we can have plenty of parameter space without getting into X-ray constraints by using this new interaction. Of course, this is obvious that relic density depends on the interacting rate times mixing angle. If we can increase the interaction rate, then we can have the relic density by decreasing the value of the mixing angle. So this was the result that was given in this paper, and there is other work which has given the relic density by taking into account vector mediators and others. Okay, so now what we have learned is that Hubble tension solutions prefer specific value of effective coupling. These are the values, and this can be translated into the couplings on G phi and M phi. And a sterile neutrino dark matter requirement using what I call as modified Dodelson-Vitro mechanism also requires the self-interacting neutrino of a particular coupling. So we just did this, we tried to explore, can we have the parameter space of KeV sterile neutrino dark matter by specifically considering this coupling that is allowed by Hubble tension solution. Okay, so we have done the similar exercise. So first we just tried to lower the value of the mixing angle, because that is one obvious choice, that if you can lower the value of mixing angle, you can accommodate very high value of coupling. So we have done this. So these are the regions that we were interested in, MI new region and SI new region. And these are the constraints that we have taken. This is the constraint that is coming from IceCube data, 7.5 years of data. And this is the constraint from tau decay. Actually, we have been considering only tau electron to do this analysis, because this is the only flavor that has some substantial parameter space left after taking into account various laboratory and cosmological constraints. So we can see by lowering the value of coupling, okay, we understood, the guess was that, okay, we can have some parameter space which can align with moderately interacting region of the self-interacting neutrino. So, and then we also tried to see whether if the sterile neutrino dark matter does not accommodate the entire dark matter of the universe, and it is just some fraction of the universe. But apparently, if you decrease the fraction of the KeV sterile neutrino dark matter, then you are going away from the this moderately interacting region. So this was the guess that we can have these common parameter space. So based on this, we had done the entire scanning of the mixing angle in a wide range from 10⁻⁻⁶ to 10⁻⁻21, and keeping the sterile neutrino from 1 to 1000 keV. So this, and we had, while we were doing this, we just specifically took the coupling which is allowed by Hubble tension, and we also removed this coupling because of this is coming from the constraints from tau decay, and this is coming from the constraint, this is coming from BBN constraint. So by taking all other values except this and using the ballpark of Hubble tension requirement values, this is so what we see, that this is the parameter space, the white region, this is the overproduction region. Okay, these pink lines, vertical lines, and here the pink vertical lines corresponds to underproduction region. This white region corresponds to the parameter space where we can explain the sterile neutrino as dark matter. So while doing this, we also got the reference. There is integral data, which they have basically taken the entire 16 years of X-ray data. They have done the analysis of 16 years of X-ray data, and they have given these constraints which are going even towards smaller and smaller value of sin square theta. They're pushing it towards, let's say, 10⁻⁻18. And we considered these constraints, and we saw that fortunately all the interesting parameter space is free from these X-ray constraints. So just for the comparison, we superimposed the results from this Sen et al.'s paper, which was the original paper, and we compared our results with that. And this brown region is the result from this paper. And we have seen that we are going towards smaller value of sin square theta, which is obvious. But here in the high neutrino mass regime from 50 to 1000 keV, when we are constraining this integral data, our parameter space is entirely free from these constraints. So this is one difference that we had seen. So, and also this particular, these constraints had been obtained for muon neutrinos by taking into these constraints. Our constraints are actually obtained for tau neutrinos. So this is the thing. So now, while we are doing this analysis that of this sterile neutrino going to KV dark matter, so we understand that if we consider this new mediator can decay into active neutrino and sterile neutrino, and we have to ensure that this decay should happen. This decay should be such that it would not increase the relativistic degree of freedom, because we want to have delta n effective less than 1. This has been constrained very well from CMB observation. So we tried to see what is the limit on the mixing angle that we get from here. So this is the decay width of the mediator going into sterile neutrino, and this is the parameterization of the interaction rate to the Hubble expansion rate. And we can see that we have to actually we have to choose very small value of sine square theta. We have to keep our mixing angle like 10 to the power minus 15 or 16 to ensure that this thermalization doesn't happen and we don't disturb the delta n effective constraints. So we choose the value, we need to choose the value of sine square theta 10 raised to power minus 14, which is in agreement with the values, the range of values that we are getting from this parameter space. So okay, so basically now we know that this phenomenological model that we are considering, we need standard model neutrino mass of around this 0.1 electron volt, and we need keV scale mass of right-handed neutrino, and we need very tiny mixing angle, which actually depends on the Yukawa coupling of neutrino. So this kind of very different spectrum that wouldn't be possible if you consider standard type 1 and type 2 seesaw scenario. And the other constraint that we are getting is that we cannot have, this has been already discussed in the one of the papers, that we cannot have Dirac nature of standard model neutrino because this will disturb this constraint. So we basically need a very different kind of theoretical framework where we need Majorana nature of standard model neutrino, very tiny Yukawa, very tiny mixing angle, and keV scale mass of right-handed neutrino. So so we tried to see whether we can have something in theory where we can explain all these things. So generally, to explain neutrino masses, we need higher dimensional operators that we use. So we need higher dimensional operator, dimension 5 operator, and dimension 6 operators. So we have tried to to explore these higher dimensional operator in the context of supersymmetric framework. Generally, all the term that we write in the Lagrangian in type 1 seesaw, that is written in superpotential. This is the neutrino Yukawa coupling. This is the Majorana mass of right-handed neutrino. And if we take the supergravity framework, we have superpotential and we have Kähler potential. So we assume that this is there is a good assumption that you can have a global symmetry in which you can assign this. These Xis are the hidden superfields which actually give us the scale of supersymmetry breaking. So we can assign some charges so that we can cancel these couplings in the superpotential, and we can write these couplings in the Kähler potential from higher dimension operator. So this is one operator where hidden sector field interacts with right-handed neutrino, and this is another field where this sector interacts with left-handed neutrino, because we are trying to produce the Majorana nature of we are trying to produce the mass of a standard model neutrino also by considering Majorana nature, and this is the interaction coupling that we can have from higher dimensional operator. And we would see, if we do the supersymmetry algebra, we would see that this first order non-renormalizable term wouldn't give us the mass of right-handed neutrino and mass of left-handed neutrino, and that we can go from the further next level non-renormalizable operator, which is 5-dimension and 6-dimension operator, and we can get the Majorana mass of right-handed neutrino, which depends on F term of SUSY breaking scale and wave of Xi, similarly for the standard model neutrino. And this is the neutrino Yukawa coupling that we get. So now, and this is the mixing angle. We can calculate the mixing angle from this neutrino Yukawa coupling. So now if we fix this Fx to be 10 to the power 22 GeV, this will give the mass of supersymmetry breaking scale around order 10 TeV. And we have fixed this mass, fixed the wave of the X around 0.001 MP. So we can see that with this range of order 10 TeV SUSY breaking scale, we can have this hierarchy of masses. We can have KeV right-handed sterile neutrino, 0.1 eV left-handed neutrino, and the Yukawa coupling and mixing angle that we need to produce the right relic abundance of sterile neutrino. So this is the summary. So basically, we understand that there is intimate connection between KeV sterile neutrino dark matter and self-interacting neutrino, and that will give us new mechanism, which is to find signatures of warm dark matter, which would be cosmologically motivated. We can have similar picture with the mixture of axions by considering the superposition of axions with neutrinos. And the observation from next generation of cosmology experiments can even more validate this parameter space. And now, while we were considering this range of G effective from cosmology, it was assumed that the entire region was radiation dominated, from high redshift to even low redshift around 10 to up to 10 to the power 2. The entire region was radiation dominated. We can see what is the allowed range of G effective if you consider the intermediate range to be matter dominated, because that is also interesting choice of alternate CDM models. So, and as we have in the first talk by Tirthankar, we have seen that WDM candidates are popular choice that can impact the global signal for 21 centimeter observation. It would be interesting to re-estimate the bounds and reconnect this by considering self-interactions of active neutrinos. And in general, this can lead to new roadmaps and need to be studied thoroughly in theoretical frameworks of physics beyond standard model. Thank you.
Thank you, Mansi, for that excellent talk. I have questions now.
Less particle physicist.
I can ask you a question. For this model, why did you have to go to a Sugra framework? What does that scalar potential get you?
No, this is, I mean, first thing is that this was a choice, but I had tried normal type 1 and type 2C framework. So type 1 and type 2 seesaw.
No, my question is, supposing you just take SUSY and just add that superpotential term,
Okay.
W.
We cannot have non-renormalizable operators in superpotential. So if
you are getting the non-renormalizable operators from that.
From Keller potential, yes. That is difficult to get. Even it is all holomorphic, so you cannot have this kind of coupling which you can. Superpotential is holomorphic. Yeah.
Yeah.
Yeah. So while calculating the relic density of the sterile neutrino, so I mean, what is the phase space density distribution F of sterile neutrino? What is it assumed? I mean, how you fix this phase space?
So there is a distribution of standard model neutrino, normal Boltzmann distribution that we have assumed. So we have just used that to calculate, because if I just go and see this expression. Yeah, so this is the thing. So I haven't written the expression of this distribution, but the phase space, this distribution as a function of temperature entirely depends on the distribution of active neutrinos. So we have been actually considering only the distribution of active neutrinos, and we are getting the distribution of sterile neutrino by considering the probability as well as the interaction rates.
Okay, but if I assume that this sterile neutrino is is being produced from in non-thermal process. Okay.
Yeah, then
so
then we have
how we can then
I
estimate
mean, of course, then if it is thermally produced, then you can have normal Boltzmann distribution function. If it is non-thermally produced, then let's say it is getting produced from the decay of some heavier particles. So then there are different ways of calculating the relic abundance that we will see that where that heavy particle gets frozen in the early universe, and whatever number density it gives. So that from there you can calculate this. So that is different method to calculate. There are methods to calculate that, but that would need, first of all, that would need that heavy particles or some new particle which could be used.
Yeah. Okay. Thank you.
Hi, Mansi. Good talk. Nice talk. You probably mentioned this, but there are constraints on self-interacting neutrinos from supernovae, right? As in neutrinos in the proton
those
neutron star.
constraints are for small mass of mediator.
Okay, strong
So there are,
self-interactions.
so this is taken to be from, if I remember, there are constraints from supernovae, but we are not considering that region. And similarly, for mass of sterile neutrino, those constraints are on electron volt mass of sterile neutrino. This is KeV, so we can exclude those constraints.
Okay. So I had a similar question. I think your answers that already, which is people are trying to constrain the self-interactions from supernova neutrinos hitting relic neutrinos on the way. That way you see some deficit in hyper K and so on. But I guess it's the same. It's the same story.
So there are, in fact, this Sen et al.'s group, they have done the same analysis for low mass of mediator also, where they are actually taking into account the supernovae constraints as well as the effect on relativistic degree of freedom. So
Thanks.
Because I have just taken a specific.
Right.
I see no more questions. Thanks, Mansi.